Hi everyone, let's go over parts of the handout regarding polar coordinates and rectangular coordinates and also parametric equations. These tend to be a little bit harder for people. This is due on the 26th, so we have a few days yet. So as we go through this, just remember there are specific conversions for x and y in polar coordinates, and there are specific ways to do what's called parameterize and not parameterize an equation. Okay, and so basically with polar coordinates, we're dealing with things that are circular. With parametric equations, we're dealing with points along a curve and finding the exact point an object is at any given second. Okay, so let me share the screen with you, the handout that I sent out a couple of days ago. And let's talk about a couple of problems here first. So let's see, let's talk about A and let's talk about B here, and then I'll have you worry about C. I'll give you some hints on C, but I'll let you worry about it. Okay, so first off, this first number is the radius. So think about these as a circle. So think about the rectangular coordinate system as a big target with circles of certain radiuses. Okay, that's my cat, so don't worry about it. So we have a radius of 2, and we want to go to 3 pi over 2. So here's our radius of 2. So there's pi over 2, 2 pi over 2, 3 pi over 2. We stop there. Okay, the second one here is 5 pi over 3. So this is the radius of 3. So we start here at 3, and we go 1 pi over 3, 2 pi over 3, 3 pi over 3, going along that circle, radius 3, 4 pi over 3, 3 pi over 3. And then when the radius is negative, we start here. These are all positive radii. Okay, so over here, these would be positive radii as well. So when it's a negative, I'm sorry, these are negative radii. So when it's a negative radius, okay, there's positive 1. That's the opposite. So start here, and then we're going to go 3 pi over 4. So we'll go pi over 4, 2 pi over 4, 3 pi over 4. So we end up there. Okay. So now let's take a look at converting to polar. So first off, now my dog has my notebook. There we go. First off, we have the function or the expression, the equation at 3x squared minus y squared equals 5. The conversions for polar are always r equals cosine theta. I'm sorry, r cosine theta equals x. And for y, it's r sine theta. So wherever you see a x, you're going to replace it with r cosine. So since it's x squared, it's r squared cosine squared and multiplied by 3. Then it's minus y squared. So y, remember, is r sine theta. So that means it's going to be r squared sine squared theta. Now these both have r's in them, so we'll factor the r squared out, and we'll write it as 3 cosine squared theta minus 5 sine squared theta. That whole thing equals 5. Divide both sides by the 3 cosine squared theta minus sine squared theta, and we get r squared. The idea here with polar coordinates is either to solve in terms of r, or sometimes we just have to solve in terms of r squared. So the function is usually r equals and then some expression in terms of theta. To graph a polar function, okay, there are several types of graphs. The more circular they are, the closer they are to r equals a constant. The less circular they are, the further away they are to that. So when we have a function r equals a sine theta plus a, where these two numbers are the same, or we could have a cosine theta here as well, it's called a cardioid. It's kind of heart-shaped. So typically with these, you can pick as many points as you want going around the circle. I typically pick 0, pi over 2, pi, 3 pi over 2, and 2 pi, just to see what it looks like. I have an idea what it looks like. I know it's heart-shaped. So when I plug 0 in, we get 3. We plug pi over 2 in, we get 6. We plug pi in, we get 3. 3 pi over 2 gives us 0, and then 2 pi gives us 3 again. So starting at A is 3. So there's our point A. That's our first point there. Then for point B, we're at pi over 2. So here's pi over 2, and we have a value of 6, so a radius of 6. Going to theta, or to theta equal pi, here's theta equal pi. We have a radius of 3. So far we know they connect something like that. And then When we get to 3 pi over 2, we have a radius of 0. So that stays right there at the origin. So that means this has to come in, fold in like that. And then to close it out, at point E at 2 pi, that's back over here on the positive x-axis, we end up at 3 again. Now again, you can do that all with the calculator. You have to make sure your calculator is in polar form. And I would make the window, and have a good idea what kind of a graph it is, because there are several graphs and they'll go through that. But have an idea what kind of graph it is. And even if you don't have an idea what kind of graph it is, just kind of plug in the axis points of 0, pi over 2, and 3 pi over 2. And that will kind of give you the max and mins typically of these things. Okay, so I look at another one. This one is a parametric equation. What's a parametric equation? It's in terms of time, or t. So for parametric equations, I typically have an x value and a y value. When I put the two together, it traces out x and y points on a rectangular coordinate system. So with these, you also can graph them with your calculator. Okay. With your calculator, you have to make sure the mode is in parametric function mode. And then you'll have an x of t and a y of t. When you plug this in, the calculator will graph the direction the particle is going in. Okay? So in this case, when I plug 0 in, the cosine of 2, 0 is 1. 3 times 1 is 3. So at times 0, x is 3. But what's y? Well, sine of 0 is 0. So y is 0, so it's on the x-axis. Okay. Then when I go to pi over 2, I plug pi over 2 in. That's cosine of pi, because the 2's will cancel out. Cosine of pi is minus 1. Minus 1 times 3 is minus 3. Similarly, when I plug pi over 2 in, the sine of pi over 2 is 1. So sine of pi over 2 is 1. Okay. 1 times minus 3 is minus 3. So that gives us the point minus 3, minus 3. Okay. And then so on. So that goes, so if I'm here, okay, I'm going to go minus 3, minus 3. So it's going to be 3 down and 3 over. So that's someplace over in here. So it keeps going on like that. Okay. And then just keep plugging in. Okay. And so what happens is if you plug it in or you look at the graph, it's going to go like this for half of it, and then the other half is going to go like this. So it kind of bifurcates a little bit. It's not a continuous movement of the particle. This one is. So x of t equals t, and y of t equals t squared minus 1. When you have a scenario like this where you have one of the variables defined just as t, is happy days, because then you make that variable equal to t, and then you substitute that variable value in for t in the other function. So in other words, since x is t, I can substitute x in right here and make it x squared minus 1. So that tells me that the rectangular version of this is x squared minus 1. X squared minus 1, parabola opening up, slid 1 unit down on the y-axis, and the particle is going to travel from left to right in a continuous fashion from minus 2 to 2. Here's some other practice. I'm going to graph r equals 3 cosine theta, so this is back to polar. And again, I'm choosing my points, 0, pi over 2 pi, 3 pi over 2, and 2 pi. So when I plug 0 in, cosine of 0 is 1. 1 times 3 is 3. So we're at a radius of 3, 0 for an angle. When we plug pi over 2 in, that's over here. Plug pi over 2 in, the cosine of pi over 2 is 0. 0 times 3 is 0, so that stays right on the origin. When I plug pi in, pi is over here. So going over here, how to get back over here? Well, let's find out. So let's see. If I think about, okay, cosine of pi is minus 1. Minus 1 times 3 is minus 3. So this is the positive 3 direction. Minus 3 will be the opposite direction. So that gets us back here. So we've gone from here over to here. And now we're going back again. So we do 3 pi over 2, we're back to 0. And then when we do 2 pi, cosine of 2 pi is 1. 1 times 3 is 3. So we're back here. So it makes a nice circle. And again, you're going to do this with your calculator, so it's not going to matter. And then to convert, let's take this rectangular function and let's convert it. We have, let's convert rather this polar function to rectangular. We have 2r sine theta plus 3 and r squared cosine squared theta minus 4. So anytime we see an r sine theta, it's a y. Anytime we see a r cosine theta, it's an x. Since r squared cosine squared, it's all squared, it'll be x squared. So we have y plus 3 over x squared minus 4. I'm going to multiply both sides by x squared minus 4, giving us 2 times the quantity x squared minus 4 equals y plus 3. Moving the 3 over, we have 2 times the quantity x squared minus 4 minus 3. Distributing the 2 gives us 2x squared minus 8 minus 3, which ends up giving us y equals 2x squared minus 11. Now, the other thing you'll have to be able to do is convert back and forth polar and to rectangular. So anytime we have something in polar coordinates, we want to convert it to rectangular, we use the expression r equals cosine theta for x and r equals sine theta for y. So suppose we have the point 2,3. Okay, so we got to think about that as a point 2,3. Since it's a point 2,3, I make a line from the origin to the point 2,3 and create a right triangle. I find out the length of the hypotenuse from the origin to 2,3. In that case, it would be the square root of 13. So that means r is the square root of 13. Okay. And then I need to find the angle. So what's the angle? The angle then, I would use an inverse cosine or sine and figure out what the angle would be, or an inverse tangent if I had to. Either way, you get the angle. That angle then tells you what theta is. So we have r and we have theta. If we want to convert that back to x and y, we just plug r in and theta in and evaluate. Our cosine theta, that value will give us x, and our sine theta, that value will give us y. Okay. So hopefully this helps out a little bit. Have a good day.